Okay, Trig fans, we are back with lesson 4, which is trig derivatives part 2. And so today we're going to refresh and reconnect you with implicit differentiation and look at how that applies to trig derivatives. So here we go. So the first thing you'd want to do is just let's refresh our memory of implicit differentiation. Now, if you need help with implicit differentiation, great, this is for you. And if you don't, you can skip through this first guy. So remember, the derivative of 12 with respect to x is 0. This is product rule right here. So the derivative of x is 1 times y plus x times the derivative of y. And the derivative of y is y prime. Plus the derivative of x is 1. And then this is going to be the derivative of y is 2y. And the derivative of y would be y prime. So there you go. And then what I'm going to do is I'm going to take all the terms with y prime to the other side. I'm going to factor out a y prime and divide the other side by whatever's left over, which in this case would have been an x plus 2y. So that's implicit differentiation. If you need more than that, come see us. Now let's look at it as it applies in this section here. So the derivative of sine x would be cos x. The derivative of sine y would be cos y times y prime. Subtract the derivative of cos y is negative sine y times the derivative of y, which is y prime, equals 14. And once you have it in that form, take all the y primes to the other side and then divide by what's left over. Now, not to worry here, we're gonna look at this in detail here. Okay, so let's try the tiger. Pause the video and give it a go. All right, here we go. So this is going to be the product rule right here. So the derivative of x is 1 times sine y plus x times the derivative of sine y is cos y, and the derivative of y is y prime. Plus, now be careful here, the derivative of cos bracket x plus y is going to be negative sine x plus y, and now we need to multiply this by the derivative of x plus y, which is 1 plus y prime. So be careful here. We're going to keep all the y primes on this side. Notice that when we expand this out, this is going to be 1 times this whole thing, and then it's going to be y prime times this whole thing. So when we do that, it's going to be negative sine x plus y plus negative y prime sine x plus y, and keep all the y primes on one side, keep everything else on the other, and finish it from there. Alrighty, so now what we're going to do is our goal is to get to this question, which is determine the equation of the line that is tangent to the curve sine x over cos 2x when x equals 1. Now, first off, I hope you're thinking Desmos here. I hope you're thinking of answering in Desmos so you can see what that curve looks like and see what the line looks like. If you're not sure how to begin that, this is a nice warm-up question, which we did in chapter 2 of calculus, which was derivatives. Determine the equation of a line that is tangent to the curve y equals x squared at the coordinates 3, 9. So the first thing we're going to do is take the derivative there. We are going to put 3 in for x, and that just means that when x equals 3, the derivative is 6. So I know for sure that the derivative here is going to be y equals 6x plus something. But what's the something? Well, remember that this line here has to go through that point. And if this thing here goes through that point, that just means that when I put 3 in for x, this side here has to equal 9. And now I need to find the y-intercept that makes that true, because right now I have 9 equals 18, which isn't true. So that must mean that b equals negative 9. What I'm going to do is go ahead and graph this just to make sure that it's true at Desmos. And so here is our parabola. Let's put it in a view that we can see a little bit better. There's my line. Man, that sure looks like we got it. And there's the coordinate at 3, 9. There's the tangent line, and there's the curve. So it looks pretty good to me. So let's take a look at this guy. And this guy looks tricky. So first off, let's take the derivative. Derivative of sine x is going to be cos x times cos 2x minus sine x times negative sine 2x. And then the chain rule. Don't forget the chain rule times 2. Now, I've simplified it here a little bit, but remember, now what I'm going to do is I'm going to put x equals pi in for all those x values, because when I do that, I know that the cosine of pi is -1, and the cosine of 2 pi is +1, and I know that the sine of pi is 0, and the sine of 2 pi is 0, and so on. So we know that from our trig function section, and if you're not sure of that, please draw a cos wave and a sine wave to help you visualize that. So what that means is we know that the slope is -1, and so I have the y equals -1x plus b. And what I now need to do is figure out what this other y value is, which we wouldn't know yet. And to do that, I'm going to take the pi and put it in for sine x. So the sine of pi is 0 over 1. Oh, 0 over 1. Y equals 1. So then what I'm going to do is continue this, and b is equal to pi. So then what I'm going to do is graph this in Desmos just to help visualize that. So here's Desmos. That's not the graph I wanted. Oops. Let's go back. That's the graph That's the graph we wanted right there. Okay, so most of us probably don't know that that's what this graph looks like. And it's kind of an interesting graph. Just for funsies, I did that or this. I wasn't expecting that, and neither were you probably. Now, remember, what was that equation again? The slope was -1. Oh, I guess we should get the coordinate first. So let's type in the coordinate. So that's going to be pi comma 0. So we're talking about what's the slope right there. And gosh, to me it looks like -1, which is what we found. So it's going to be -1x. And now how much do I need to move it up? Well, I think in our equation that we were looking at, it was the y-intercept was pi. So I'm going to put pi, and there you go. Look at that. That is the slope there for sure. And there's the equation of the tangent line. That is a tricky question. Let's come back to our last challenge. And in this case, a graph is given. Here's the equation, x minus cos x. And they're just asking for some terms here. So this was from our Maximin chapter where we were learning about critical numbers, and critical numbers occur when the slope is 0 or undefined. And I see a bunch of zeros in there, so that's what we're going to look at. If you need a stronger review of intervals of increase and decrease, you could click on this link right here and sort of walk through this and look at critical numbers and their definitions and all those sorts of things. But I think for many of us, we are going to be okay. So remember, in order to find the critical numbers, you just need to take the derivative of the function, set it equal to 0, and then find those values. And this one said between -2 pi and pi, and those values would be, let's see, right there and right there. So there are the 2 times that it's 0 in that region. When is this thing increasing and decreasing? Well, I don't know if you can tell, but this look is increasing the entire time. And if we were wondering how we could know that, we could test values in between -pi and 2, -pi over 2 and 3 pi over 2, and we place those values in here. And if the value is positive, which it's going to be because it's increasing, then it's increasing on all fronts. Okay, and then the point of inflection, well, that happened when it was in between concave up. So here's concave up right here. Here's concave down. So somewhere in there, there's going to be a point of inflection. There'll be a point of inflection right there as well. So there's a number of points of inflection. In fact, you can see that this is concave down, this is concave up. So there's actually a point of inflection right there as well. And this is concave up and this is concave down, so it would be in there as well. And the way we find that is by taking the second derivative and setting it to 0 and determining when is it 0. And so that's where these values have come from. Here are the x coordinates, and the point of inflection has an x coordinate and a y coordinate. So that's pretty tricky, no question about that. Here's what the graph looks like. Not sure what I was looking at there, so we're just going to come back here and call it a day. So don't forget to make an entry in your digital portfolio. You can make any entry in your digital portfolio. You are gathering information that you can successfully make these curricular competencies part of your practice. Okay, there are some great questions in the text to try, and don't forget to try those go formative questions. They are essential.